Hi guys, welcome to my channel. Today we are going to discuss about the trabecular system of femur. Yes, as we discussed, we are going to discuss about the structural adaptation to weight bearing in hip joint. You know that earlier I have told you the primary function of the hip joint is weight bearing. That is the unique and primary function of the hip joint. So when the weight is transmitted to the hip from the upper part of the body, often denoted by the term hat, not the hat on your head, but head, arm and trunk, it can produce lot of stress in the hip joint. So this stress has to be balanced by some mechanism, and that mechanism is what we are going to discuss. So there are some structural changes in response to weight bearing. Okay, we are going to see one by one. Before that, what is the weight that is transmitted to one hip joint? The weight that is transmitted to one hip joint is the weight of the hat, not exactly half the weight of the hat. So one hip, right hip is having half HAT, left hip will have half HAT. Clear? Because both are simultaneously affecting in the or taking part in the weight bearing activity. So this is the femur, this is the head of femur, this is a trochanter, this is its neck. So the weight is transmitted like this. That weight is denoted by the representation half HAT. There is always an additional force that the ground act, and that force is known as ground reaction force, GRF, ground reaction force. So this both force, if we evaluate this, both force can be extended like this, and they are parallel to each other. They will have a momentum which is equal to the perpendicular distance between the force. This is the momentum of the force. We have earlier studied that two forces which are parallel and opposite to each other can form a force couple. So that act as a force couple, and unique function of the force couple is they can provide rotatory motion. But in hip, is it providing rotatory motion, or can it provide rotatory motion? If it is providing rotatory motion of the hip joint, rotation of the femur, it can result in various problems. So this has to be balanced. How is it balanced? In addition to this, you know that here we have the acetabulum, and this part is completely compact. So this force can produce a compressive force over this side, compressive force. It can compress the bone like this. Whereas here it is relatively free, and it can produce, or it does produce, a tensile force. So there is a tensile force, there is a compressive force, there is a force couple. So all these things that are like first one, half weight of HAT, second one, ground reaction force, third one, the force couple generated, fourth one, the tensile and compressive force has to be balanced. How? And that answer is the structural adaptation. Let us see what are the structural adaptation to weight bearing. So hip joint or femur has a unique system of things known as trabecular. What are trabecula? Trabeculas are calcified plates of bone, calcified plates of cancellous bone. You know there are two types of bone, cortical and cancellous bone. So in cancellous bone there is calcified plates, and that calcified plates are known as trabecula. What is its peculiarity? This develop in response to stress of bone. So in areas of stress, this trabecula are developed. If stress is higher, more trabecula are formed, and it is represented by Wolff's law. You know what is Wolff's law? Structural adaptation, or the form of the bone. depends upon the stress that is being faced on the bone. So if bone is having more stress, it will adapt, it will remodel in such a way this stress has to be balanced. So that is the mechanism. And for that there is a structure known as the trabecula which helps the bone in that activity. That are the trabecula. They are simply lines of bone, calcified lines of bone in various directions on response to the stress. So there are trabecula which are calcified plates of bone developed in response to stress and seen in areas of stress and increase in number if there is more stress, represented by Wolff's law. Okay. Now in hip joint, in the femur, there are two sets of trabecula, two major trabecular system and three minor trabecular system. Two major trabecular system are medial compressive trabecular system, lateral tensile trabecular system. So in hip joint there are two primary, that is two major, that's the major function, that is the medial compressive trabecular system and lateral tensile trabecular system. Minor is known as secondary compressive trabecular system, secondary tensile trabecular system and trochanteric system. You will understand when I draw the diagram. So you know that first one it is, let us see the medial compressive. Medial compressive trabecular system arises from the medial aspect of shaft. Okay, they arise from this direction point and they transmit to the superior part of head. So this is how I told you, calcified plates of bone. This is how they are oriented. Medial trabecular system. So they arise from the medial aspect of the shaft and they move into the superior of the head of femur. Whereas second major one is lateral. So this arises from the lateral aspect of shaft. And they arise from here and they have unique orientation. They are oblique. Let me draw with this color. They are oblique. They will draw like this. We'll draw it like this. Draw like this. Okay. They are like this. Clear? Let us call. They arise from the lateral aspect of the shaft to the inferior of head. Inferior aspect of the head. So two trabecular system major. One is medial trabecular system, compressive, medial aspect of the shaft to superior of the head. This one from the lateral aspect of the shaft to inferior of the head. These are oblique, this is compressive, this is relatively vertical or bit vertical. Okay. And what is the function? You heard the word medial compressive. So it will act against compressive load stress. Lateral tensile, this will act against tensile load. So it is very simple. So we earlier discussed that this area has compressive load, this area has a tensile load. So in order to compensate this compressive load, this medial trabecular system is developed. In order to compensate this tensile load, lateral trabecular system, lateral tensile trabecular system is developed. Then three minor is there, no? They are not having much similar functions, a significant function, but let us see that. That is secondary compressive trabecular system, secondary tensile trochanteric. Easy one, trochanteric, that is here. If there is some load on the trochanteric region, that is the trochanteric system. And here there is the secondary tensile. This is the secondary tensile. Here you have the secondary tensile. And in this direction you have the secondary compressive. You don't have to study the origin and insertion of this one. You have the secondary compressive. These are insignificant because they don't have a significant role. All the major role is done by the major trabecular system. So minor trabecular system is trochanteric one. here on the trochanter, greater trochanter area, then secondary compressive over here in the opposite direction of my primary compressive or medial compressive, then secondary tensile exactly in this direction in the near the neck of the femur. So you see there is an area over here. Here there is no trabecular system, none of the trabeculars are seen in this area, and this area is known as the zone of weakness because there is no trabecular system over there, so the bone is weak over that region, so fractures can take place in the neck. Exactly it is up to this much area. Okay, let's, yes, it is like this in the neck. That area is known as the zone of weakness. So we discussed earlier that there are a lot of stress, the weight of the head, the GRF, the force couple, and tensile and compressive load, and this has to be balanced. To balance it, first adaptation is the trabecular system. The trabecular system, trabeculars are calcified plates of bone. There are two major trabecular system, three minor trabecular system. You have to name it. Medial compressive, medial principal compressive, it can be also known as, or lateral tensile or lateral principal tensile system, and three minor secondary compressive, secondary tensile, and trochanteric system. You have to study the direction of these fibers and how this is being loaded. So see all these aspects, you have the trabecular system. So whenever the force is coming, this trabecular system adapts in such a way that this force is being balanced, and there is a unique area known as the zone of weakness where trabeculars are absent. That's all about the trabecular system. Now the second thing that you have to consider is the acetabulum and femur. You know that the weight is transmitted to the spine, to the sacroiliac joint. Okay, sacroiliac joint. From there it is transmitted to the hip. This is the hip joint itself. This is the hip joint. So weight is transmitted and it reaches the acetabulum. But not all part of the acetabulum does takes place in the weight bearing. Only the superior aspect of the acetabulum, superior portion of lunate surface is taking place in weight bearing or transmission of the weight. Similarly, the superior portion of the head of the femur is taking place in the transmission of the weight. Superior region, superior part of head of femur, head of femur. Very good. So the weight is transmitted to the sacroiliac joint, into the hip joint, into the hip, into the acetabulum, and in acetabulum only the superior portion of the lunate surface takes place in weight transmission. Similarly, in femur, the superior surface, superior of head takes place in weight bearing. So what happens in certain conditions, like acetabulum is anteverted, you have seen that it leads to instability. This covering of the acetabulum decreases. So large amount of the femur is exposed. So the weight bearing is insignificant or less efficient. When weight bearing is less efficient, there is less contact forces, right? Because there is no contact between, there is less contact between acetabulum and the femur. So there is less contact forces, leads to instability. This is in anteversion of the acetabulum. If acetabulum is anteverted, or if acetabulum is shallow, what happens? That is, acetabulum is less curved shaped. So then also less articulation, less contact force, and instability. And also in females, acetabulum is shallow, we have discussed it earlier, therefore less contact force. It don't lead to instability, but there is less contact force as compared to men. Contact force means the force that is exerting between these two contacting surface. So this is a contact force that is acting on. This is a contact force. So this contact force can result in, after a long time, it can result in degenerative changes. It can result in degeneration of the acetabulum. The dome of acetabulum or lunate surface degenerates. Clear? And femur degeneration. Femur degeneration is two type. ball shape of the femur, ball shape of head vanishes. Head becomes flattened. Head becomes flattened. Flattened. So these are the changes. So there is nothing to worry. The thing is that the weight is transmitted to the hip joint and to the acetabulum. When the weight is transmitted, it is only transmitted to the superior portion of the lunate surface. And in the femur also, only the superior portion act. So if there is less coverage, then there is less contact force and leads to instability. That can be possible in the case of anteversion when acetabulum is shallow and in case of females. But in the long run, if there is more contact and there is more contact forces, it can lead to degeneration of the acetabulum and the femur as well. If the acetabulum, the degeneration can take place in the dome of the acetabulum and the lunate surface. In femur, degeneration can result in the ball shape of the femur, head of the femur vanishes or head becomes flattened. That are the changes. Now you know, between two contact bonds or contact surface, imagine this is just the femur, I am not going the trochanter and so on, this is the acetabulum, okay. There is always an articular cartilage. Here you have an articular cartilage, here you have an articular cartilage. This helps in the increasing the congruency and reducing the friction. So due to this excessive load bearing, this articular cartilage can get also degenerated. But this articular cartilage is avascular, important feature, avascular. So the vascularity, or it receives the nourishment due to this compression. So when there is compression, this nutrients gets diffused in the synovial membrane or synovial fluid. And that is how articular cartilage gets the nourishment. So when there is less compression or less weight transmission, articular cartilage can get degenerated. This happens in conditions like when we are bedridden. What happens is that there is no weight bearing. So for a long time, for 1 week or 2 weeks or 1 month, what happens ultimately is articular cartilage becomes less nourished. So since it is avascular, this receives the nutrition from this diffusion. So weight bearing is essential for articular cartilage. If weight bearing is less, the articular cartilage can go for degenerative changes. So weight bearing, this is just a note in between that. Articular cartilage. Important things are other things. And the third system of adaptation needed is the shaft of the femur. So we discussed so far what happens to the head of the femur. So you see the weight is transmitted like this, and the head we have lot of adaptation, trabecular and this all. What happens? The weight is also transmitted to the shaft. The shaft of the femur, you will see that it is not vertical, it is bit oblique in shape. We haven't discussed about various angulations. So it is a bit oblique in shape. So the medial side of the shaft is always facing compressive load, and its lateral side always has to face the tensile load. That is the same thing. Here this is the tensile, here this is the compressive. So like the head of the femur, the medial side, which is close to the body, medial compartment of the body, medial side of the body, adductor compartment, is always facing the compressive load, whereas the lateral side is always facing the tensile. It is due to the oblique nature of the femur. So when weight is transmitted to the shaft of the femur, its medial side faces compressive load and lateral side faces distractive or tensile load. So these are the mechanisms of mechanism that we have discussed so far. So if we try to summarize that, we can see first one, there is the half the weight of HAT acting, that will produce a ground reaction force, a tensile force, a compressive force. This has to be balanced. To balance that, we have a trabecular system. Trabecular system is 2 major, 3 minor. Okay, and 2 major are, you know, the names and so on. In addition to it, there is a unique weight bearing capacity of acetabulum and head of femur. Both superior aspect helps in the weight bearing. Then the weight bearing in shaft. It is also in a unique manner. Medial side helps in compressive load. Lateral side helps in distractive load. So these are the structural adaptation to weight bearing. The major structural adaptation is the formation of trabecular system, which is this much uniquely developed only in the femur. That unique development is for combating the increased stress that is happening in the femur. So due to this mechanism, lot of stress and weight bearing is possible in the femur. Okay, and in next class we will be discussing about the ligaments. I told you in this class we will be discussing about the ligament, but in the coming class definitely we will be discussing about the ligaments of femur, which needs a lot of effort and a lot of understanding capability to do. So we just thought that we will do the structural adaptation. Thank you so much for watching my channel, and I hope that all of you would subscribe to the channel and like the videos if you do like it, and definitely kindly post your comments and valuable suggestions in the comment box. Thank you so much. Thank you.